All right, welcome to ECE 203. This is a video lecture on electrocardiograms, and we will discuss an electrical model of the heart. And the reason for doing this is so that we can introduce instrumentation amplifiers and how to best design them once we understand how these actual systems work in the body. So if you're following along at home, reading chapter 20 in the Sarpeshkar book, particularly sections 20.1 and 20.2 are actually very well described sections on that's going to cover the material we're going to cover in this lecture. Of course, there are many other references on mechanical and electrical behavior of the heart that you can also look up on your own. So the reason we're doing this is we're trying to, in this course, develop instrumentation to instrument electronics and measure behavior of the human body. Okay. Now it turns out that the human body generates a lot of electromagnetic activity, and we can pick this up with electronics in, well, the usual ways. Now this usually happens through movement of charged particles within the body, and so a lot of the electrical activity in the body is because of ions shuttling around between and around cells. So ions are charged particles. As they move, they generate electromagnetic effects, which we can then pick up with external electronic equipment. Okay. Now, of course, that's one way of measuring how the human body is functioning, the physiology of the body, if you will. There are, of course, many other types of ways to measure signals in the body, including through means of measuring things like through physical deformation, through optical means, and so on and so forth. The focus of this lecture and predominantly this course is on electrophysiology, and that is related to the movement of ions inside the body. And in particular, we're going to place a certain amount of emphasis in this course on non-invasive means. And what we mean by non-invasive are devices that do not invade or penetrate the body. Okay, so not implantable devices, but things like wearable devices we're going to focus on a lot. We'll also talk about implants, of course, but for the purposes of the next several lectures, we're going to focus mostly on non-invasive types of measurements. So there are many types of non-invasive measurements that we can consider in this course. The one that we're going to focus on mostly today is the electrocardiogram. This is abbreviated as ECG or EKG. EKG comes from the German spelling of the word. What you'll typically find, this isn't totally correct, but in Europe they tend to use EKG as the acronym, and in the US we tend to use ECG, although it's very loose and people use both, and it's understood what both mean. And so I won't belabor the ECG point. I want to just briefly introduce some of the other modalities that we may consider measuring before getting back to ECG, which we'll talk about in great detail in this lecture. So the ECG is a measurement of the electrical fields that get generated by moving charged particles in the heart. Moving charged particles also generate magnetic fields, and so we can technically measure magnetic fields of the heart. We call this magnetocardiogram, or MCG. This typically is much more difficult to measure than ECG. As we'll see, ECG we can easily measure with just some fairly basic electrodes, whereas MCG needs very sensitive magnetic field sensors that operate in Earth's field, or actually typically we do these in very shielded environments so that we're not being influenced by Earth's field, because the amplitude of magnetocardiograms are something on the order of like picotesla type of heights, and as a result we need magnetometers that can really measure down to these extremely low magnetic fields. It's a very challenging problem. We actually in my research group have some work going on magnetocardiogram type of devices. There are other types of non-invasive measurements we may be interested in measuring. There's phonocardiograms, or PCG. This is recording heart sounds resulting from the vibration of the opening and closing of the heart valve. This is a little different than echocardiogram, by the way, just keep that in mind. There's another vital sign that's actually arguably the vital sign when you go into a hospital. This is one of the first things they do, and it is photoplethysmography, or PPG, otherwise known as pulse oximetry. And this is measuring the oxygen concentration inside of blood. Okay, and it's actually a really interesting measurement. It's a perfect example of how bioengineering and electrical engineering kind of come together to provide a very useful solution. And it turns out that measurements are performed by realizing that oxygenated blood is composed mostly of oxyhemoglobin, which we would call blood red, and does not absorb red light very well. While on the other hand, deoxygenated blood is mostly composed of deoxyhemoglobin, which is dark red and does absorb light more. Okay, so the measurement can be performed by shining a red LED through the finger, where a good artery that is not too far below the skin is located, and measuring what we call the path loss at the other side of the finger using a photodetector. Okay, now there's complications on how to do this with precision and accuracy. There's changing light conditions, absorption by skin, bone, etc., absolute relative concentrations, but they can be solved through a variety of means, knowing that the heart beats at regular intervals and so on and so forth. But basically, the ultimately this technique involves optical sensing, where you shine that LED through the finger and you measure the characteristics of the blood in that way. There are many other types of non-invasive measurements. Electroencephalogram, or EEG, is similar to ECG, although in this case trying to measure the electrical activity of the brain. There's magnetoencephalogram, or MEG, which is just like MCG is to ECG. This is the magnetic measurement of brain function. Now, this is even more challenging than MCG because the magnetic signatures that come from the brain are on the order of femtotesla type of levels. And so we really need super high performance magnetometers in order to measure MEG. Okay, and so what we're showing here is colloquially what I like to call the upside down toilet bowl. But what's actually happening here is this is a liquid-cooled squid sensing array, which is basically superconducting coils that are cooled to the point where they're superconducting, and they can pick up these very faint magnetic fields. This type of measurement typically has to be enclosed in a very, very well shielded room to shield the devices from ambient magnetic energy. There's all sorts of other types of non-invasive physiologic measurements, electromyogram measurement, or EMG. This is the measurement of muscle function. Electrooculogram, measurement of eye motion. Electrical impedance tomography, or EIT. This is measurement of impedance to infer tissue composition. It has various uses. And then, of course, there's other types of non-electrophysiology measurements related to ultrasound, magnetic resonance imaging, blood pressure measurements, temperature, and many more. Okay, so we're not going to talk about those. What we're going to focus on today is ECG. All right, so as I mentioned, the focus of today's lecture is ECG, or electrocardiogram. And this results because every time the heart beats, it generates a spatiotemporal electric field that propagates through the conductive medium of the chest to the surface of the skin. And the ECG is basically placing electrodes on the chest or at various points in the body in order to measure this time-varying electric field. Okay. Now, ECG is a very old technique. It was first measured in 1901 using a elaborate setup, as you can see here: a string galvanometer, foot in the bath, hands in salt baths as well, and they could capture some sort of notion of what the electrical activity of the heart is. Okay, so that's since been upgraded and modernized to tabletop type of devices. These are still found in hospitals all over the United States and the world. Here you get hooked up with a bunch of different electrodes. We'll talk about where those electrodes should be placed a little bit later. And then the output will come out through basically a printed trace of your ECG. Of course, there's more modern tabletop devices that will now show this on a LCD display instead of being printed. But you'd be surprised, a lot of modern hospitals today still actually print out those ECGs. Now, that's what we would like to do for clinical studies, but in some cases, people have heart conditions that have very rare palpitations or rare events that we just can't reliably capture at the hospital. And so in many cases, there is a need to measure ECG over the course of longer than just a brief hospital visit. And so this is where things like a Holter monitor, invented by Dr. Holter, who actually interestingly has UCSD affiliations, which is basically a portable version of the tabletop device. And the original forms basically recorded ECG continuously for some set amount of time, and then you would have some elaborate connection to your phone, and you would basically dial back the results back to the hospital so that they could look at it. Of course, now we can just connect to the internet and download them directly. But these are useful for capturing some of these kind of more rare type of heart conditions. And more modern, we can start building these very small wearable devices that probably don't allow us to have very good clinical accuracy, but still allow us to capture some amount of information from the electrical activity of the heart that may be useful for certain diagnostic applications. So before we can go ahead and start building Holter monitors and wearable ECG devices, it's really important for us to understand how the heart is actually working and operating so that we can understand how to engineer the electrodes and the amplifiers and the specs on those electrodes and amplifiers, like bandwidths and impedances and so on and so forth, before we really get into that design. So we're going to cover how the brief electrical engineering version of how the heart works, starting with some of the mechanics of the heart. So the heart is effectively a four-chambered organ. The chambers are basically chambers of fluid, in this case, of course, blood. They are the upper right atria, the right ventricle, the left atria, and the left ventricle. Okay. Now you might say, well, the right atria is on the left on this picture here, and that's true. We in medicine, right is typically referring to patient's right, and so the doctor is looking at his or her left, which is the patient's right. So just keep that in mind as we go through some of these diagrams. Okay. Now what happens here is the right atrium receives unoxygenated blood from the upper and lower regions of the body. So this is, the head and arms, internal organs, and so on and so forth. It's passed through the body, now it's coming back to the heart. Okay, so the right atrium is kind of like the receiver. It receives, it collects all this blood. Okay, then what happens is the right ventricle will effectively pull this blood into it and pump the blood back into the lungs via the pulmonary arteries, where it is reoxygenated. Okay, so the right atrium collects the blood. The right ventricle, it has big muscles around it. It pumps that blood into the lungs, where of course we're breathing in oxygen, and that blood gets reoxygenated. Now the blood comes into the left atrium from the lungs, where the left atrium, works very similarly to the right atrium. The blood kind of collects there, and then the left ventricle, again a big muscle, will receive this and pump it to the rest of the body via the aorta. So this will go back to the head and arms, internal organs, and so on and so forth. Okay, so it's basically a circulating, system, kind of like a two-stroke engine, if you will. So what ends up happening is the right atrium and the left atrium kind of operate at the same time in phase 1, and in phase 2, the right ventricle and the left ventricle effectively pump together at the same time. So this is kind of operating like a two-stroke or a two-phase engine. Okay, so as I mentioned, it's a two-phase system. These phases actually have names. There's diastole and systole. In the first phase diastole, the right and left atria contract, and this pumps blood into the ventricles while they relax. Okay, in the systolic phase, in systole, the right and left ventricles contract and pump very strongly the blood into the lungs or the aorta, while the atrial relaxes and therefore fills with blood. Okay, so it's kind of a a synergistic operation. Everything's working in concert together. Now, separating the right atrium from the right ventricle and the right ventricle from the pulmonary artery, and similarly for the left side of the heart, are valves. Okay, so just like in a plumbing system or something like this, these are one-way valves to make sure that blood is flowing in the correct direction. Okay, so the forces of the heart will kind of make this happen naturally anyways, but the valves kind of really just make sure that there's no reverse currents basically going through the system. So it's kind of interesting. Valves allow one-way direction flow of blood. That sounds kind of similar to a diode might in an electrical circuit, and indeed we will actually develop an electrical analogy of the heart. Now, the ventricles are pretty powerful pumps. Okay, the left ventricle in particular is the biggest pump in the heart. It pumps 90 milliliters of blood every beat, and the muscles around that left ventricle are 3 to 4 times thicker than the muscles around some of the other chambers. Now, the atria, as I kind of alluded to earlier, are not very powerful pumps. They're more kind of like receivers. They'll just serve as a reservoir. Blood will just kind of naturally flow in them. There's a little bit of pumping action going on there, but they're not kind of the big pumps like the ventricles are. Yeah. So what I'd like to do here is try to create an analogy of the mechanical behavior of the heart into an electrical analogy. Okay, and so to do this, what I'm going to describe are Newton's 3 laws of motions, the electrical version. Okay, so Newton's first law says that every body continues in a state of rest or in its state of motion unless acted on by a force. Okay, now we can create a direct analogy to this in the electrical domain by saying every inductor maintains its current unless it is acted upon by a voltage source. Okay, as we know an inductor can't instantaneously change its current, effectively similar to Newton's first law. Okay, Newton's second law is F equals ma. A is of course dV dt. Well, F equals m dV dt. That looks pretty similar to voltage equals inductance times di dt, right? Newton's third law says that for every action, there is an equal and opposite reaction. Now, in the electrical engineering version, I would say, and there's dual versions of this as possible, in any two-terminal electrical element, the current flowing into one terminal is equal to the current that flows out of the other terminal. Okay, so I think these are pretty good analogies. It turns out there's duals of all of these, but let's complete this analogy by basically making analogies from various components of the mechanical model. In this case, force, we can essentially replace by voltage. Right, the voltage will force current to flow through the circuit, for example. Velocity in the mechanical model, I think, is very well represented by current in the electrical model. Mass in the mechanical model is well represented by inductance, according to the equations we showed there for Newton's second law. Compliance, which what we mean by that is 1 over stiffness, mechanical stiffness of a device, I think is well a good analogy is capacitance. Okay, and damping, what slows down mechanical motion, well, that's resistance. Okay, now there's an asterisk in some of these things here. I can say a dual version is possible. I won't describe it here, but if you want to think about it a little bit more carefully, I encourage you to do so, and I think you should be able to come up with another version that uses different electrical parameters to represent the same sort of system. Okay, so now that we have analogies for Newton's laws, as well as analogies for force into voltage, velocity into current, etc., what we can start to do here now is actually create an electrical model of the mechanical behavior of the heart. Okay, so we said that forces are modeled by voltage sources, and effectively that's what we can do. So we can say something like the right atrium, this is a pump in the mechanical domain, and so what is a pump in the electrical domain? Well, we can say it's a time-varying Thevenin voltage source. Now, we could use a Norton equivalent source if we really wanted to as well. Depends on how we want to structure our analogy. Okay, so each of the atria are going to be represented by some time-varying voltage source that's applying some sort of pumping voltage. Okay, then what we say is the voltage at the right atria is going to have to go through a valve, and we're going to model the valve with a diode. Now, what you'll see here is that the diode also has a capacitor across it, and that's to model that the valve is not perfectly stiff. Okay, so it's not an ideal diode, but it's a diode that requires a little bit of effectively charging up of the force across the valve before the valve will actually open. And so we can model this by a capacitor. A certain amount of charge has to develop across that capacitor before the diode will go ahead and turn on. Okay, so the right atrium will pump once there's enough energy, or in this case voltage, developed across the right atrium. It will go through the valve and start to fill up the right ventricle. Okay, now similarly, the right ventricle will then start to pump. When its voltage starts to go up and starts to exceed the diode rating of the pulmonic valve, then that's going to push current through the pulmonary arteries through here, which are really distributed transmission lines. So we can model them as maybe some series inductance, series resistance with some shunt capacitance that will effectively slow down the rate of flow of blood given the characteristics of this transmission line. Okay. Now, when the current comes through the pulmonary arteries and veins, it'll get to the left ventricle, the left atrium, where we effectively go through the same process. The left atrium has some pumping voltage. It has a diode. The left ventricle has a pumping voltage. It goes through the aortic valve to the body, arteries, and veins, which then comes back into the right atrium. Okay, so this is a nice electrical model of what's happening to the mechanics of the heart as it pumps. Now we can actually go ahead and build such an electrical model. What we can do is just create some effective voltage sources that are time varying, and in this case this is actually measured data from a prototype that actually one of my colleagues had built, and we're looking specifically here at the left side of the heart. Okay. Now, what's interesting here is we're showing the voltage of the left ventricle and the left atrium, and also the voltage of the body, which is measured, at the body arteries and veins point after the aortic valve. Okay, so what happens here is that the mitral valve closes at this point here. And what this ends up happening is the left ventricle voltage will start to really ramp up. Okay, it will ramp up to the point where the aortic valve will open. Okay, and when the aortic valve opens, then all of a sudden we get this change in effectively the body voltage, if you will, as measured at the body arteries and veins. Okay, now the aortic valve will open for a certain amount of time in sort of kind of like a rectifying behavior until it closes when there's just not enough energy to pass through here. So here the aortic valve closes. And that drops the left ventricle voltage until the mitral valve opens. Okay, so what's really interesting is that this circuit model is creating internal waveforms that model what's happening to the heart, and then the resulting V-body waveforms is actually very similar to something that you would actually measure. And in fact, a diagram like this is very representative of what would happen when you take your blood pressure measurement. Okay, so what's really interesting here is that because there's capacitance across these valves, what that means is that the pressure, or in this analogy, the voltage, does not fall to zero. Okay, so when the left ventricle voltage does fall to close to zero, but because there's this capacitance or finite compliance across the valves, it doesn't fall to zero. Okay, so when you take your blood pressure measurement, they always give you two numbers, right? 120 over 80 milligrams, for example. What this is effectively representing is the pressure at the height of when the aortic valve is open, and the pressure at the lowest part when the aortic valve just opens. Okay, and so if you have a very low blood pressure, this means that maybe there's something going wrong with your valves and how they're working. So now that we understand the electrical characteristics of the heart a little bit better, or sorry, the mechanical characteristics of the heart a little bit better, let's now try and understand the electrical characteristics of the heart a little bit better. So far we've seen the heart pushes blood around the body. Okay, that's essential for the body to work. But why are these pressure waves shaped the way they are? In such a case, we said they kind of look like a half sinusoid type of pressure wave. Okay, so it turns out that there's a lot of electrical influence into how this system works. Okay, effectively, how do those time-varying voltage sources get generated? Now, in a normal behaving heart, the answer to this question is effectively that there is what we call a biologic pacemaker. And this is effectively an electrical subsystem that receives feedback from various points in the body and says at various points in time, start the pumping operation now. Okay, pump, 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 etc. This is kind of like somebody at the front of the rowing team saying stroke, stroke, right? In fact, well, the heart is pumping, right? So this is a fairly good analogy. Now, the actual electrophysiology of this is a little bit more complicated, but let's take a look. So what ends up happening is the pacemaker starts at the node we call the sinoatrial node. We call this the SA node. Okay, this triggers atrial contraction. Okay, so we get some signal that comes into the SA node, and this says, okay, go. All right, and just for clarity's sake, this is the right atrium, the right ventricle down here, the left atrium, and the left ventricle down here. Okay, so this SA node will start to trigger atrial contraction. Okay, but it's a very fine system, right? Atrial contraction can't happen at the same time as ventricle contraction, and so what ends up happening is the electrical signal at the SA node starts the atrial contraction, but then propagates down this purplish system here until it gets to the atrioventricular node, otherwise known as the AV node. Okay, and this triggers ventricular contraction. Okay, so effectively the pacemaker will start at the SA node, 0.1, and this will generate a pulse. Now the pulse travels down a distributed transmission line, in this case it's in purple, and the time delay of traveling through this distributed transmission line will set up the relative pulses between the SA and the AV nodes. Okay, so how does this traveling electric wave actually trigger contraction? Okay, so what ends up happening is that when the impulse reaches what we call a cardiomyocyte, which is a cell inside the heart that is well, we can say, let's see here, the myocyte contracts, it physically contracts because of a mechanochemical property of the cell. Okay, so what ends up happening is we get this electrical impulse flowing through, and as we discussed with neurons, this electrical impulse will cause some state in the cell to change. Okay, it will change its electrical state. What happens is sodium will briefly rush into the cell. Then calcium will depolarize the cell, eventually causing it to contract when the calcium inward current is balanced with outward potassium current flow. Okay, and so effectively we get this pulse into the cell. The cell responds through an interesting mechanochemical property. It will change its electrical state and therefore contract itself. Okay, and then after it's contracted, it will repolarize itself. So let's take a look at this in a little bit more detail. So here's a very rough description of a cardiomyocyte, and we have some energy that's coming in order to activate this sodium-potassium pump. We also have a potassium ion channel here. Okay. So we have internal and external concentrations of various types of ions here. What this allows us to do is write out the Nernst equation. In this case, I'm going to use a slightly different form of it than what we presented in an earlier lecture, but it's effectively the same thing. So minus kT over Q times natural log of the concentration inside versus outside. Okay. Now for potassium, we have an outside concentration of 5.3 millimolar, inside 172. If we plug it into the equation there, we're going to get 90 millivolts, but we have to be careful. The sign in this case for potassium is negative. Okay. For sodium, we have positive 40 millivolts. For calcium, we have positive 205 millivolts, and you have to be careful here because we actually have two charges for calcium. It's a 2+ ion, and so we have to take that into account when we explore that relation. And chloride is minus 28 millivolts. Again, careful of the sign here. It's a negative ion, not a positive ion. So then we can try and figure out the cell's resting potential. So we can draw our circuit diagram here. We have some voltage source for potassium, some effective resistance associated with that voltage source. Similar thing here for sodium, Rna+. Similar thing for calcium. Nernst potential for calcium. And then a similar story here for chloride. Okay. Now all of this has some amount of membrane capacitance, C membrane, and what we're trying to do is figure out what is the overall cell potential. Now it turns out that during rest, the resistance of the potassium channel is much lower than all others. And therefore, the membrane potential at rest is effectively just or approximately equal to minus 90 millivolts, which is the Nernst potential of the potassium ion inside the myocyte. And keep in mind, this assumption is for myocytes only. This is not true for neurons and things like this. Okay. So what ends up happening? We have a resting potential of minus 90 millivolts. The cell is comfortably there, and nothing's really happening. And then what happens is that we get some sort of trigger. Okay, so this is the energy coming from, for example, the SA node or propagating through to the AV node. We get some sort of depolarizing trigger. What happens here is the sodium channels will open briefly. Now, sodium has a natural resting, or it has a Nernst potential of plus 40 millivolts, which means that if this channel's open, the resistance drop considerably, and so the intracellular potential is going to tend to go up all the way to 40 millivolts. Okay, so what we can say here is that RNA plus rapidly drops to 100 to 1000x lower than RK plus during depolarization. Okay, so the NA channel opens briefly. Then there's a little bit of mystery stuff that goes on here. At some point, calcium is in balance with the potassium coming out, and at this point, this is when the cell actually does its mechanical contraction. It contracts, then more potassium flows out, the calcium flow halts, the sodium channel resets, and we're back to our normal state. Okay, so this is really what the action potential looks like. The intracellular action potential looks like for a single cardiomyocyte. Okay, so we can look at this in a slightly well, in the same way, but with breaking down the different components here. We have an influx of sodium current right at the start here that will cause the intracellular membrane potential to go closer to the plus 40 region. So that's the depolarization phase. Then we have some inward calcium current that happens. This is when we have some repolarizing going on. We plateau for a little bit. We have our mechanical contraction, and then we repolarize further when the outward potassium current comes back to normal here. Okay, so effectively the summation of these inward sodium, calcium, and outward potassium currents effectively create the shape that we're looking for. All right, so by taking a cursory glance at the flow of ions in and out of the cardiomyocytes, we get a membrane potential voltage that looks something like this plot here. But if you think back to your experience watching TVs or movies, with somebody in the hospital, they always have these little ECG traces going on in the background, and it looks nothing like the membrane potential of a single cardiomyocyte. It looks something more like what we have on the bottom here. Okay, and so the question is, well, what's going on? This is the actual thing that's happening inside the cell, and it looks nothing like what we'd measure on the outside of the body. Okay. So the short answer here is that the first plot shows the voltage across the membrane of a single cell. Okay, but what we're actually measuring when we're measuring an ECG is not just a single cell, of course. We're not taking a sharp needle and probing the inside of a single cell. We're putting electrodes on the chest and measuring a collection of something like 2 times 10 to the 9 myocytes in the heart. Okay, and so effectively what's happening here is vector summation. Okay, so the heart must be charge balanced. We're not accumulating an excess amount of charge inside the heart, otherwise bad things would happen. So what that means is that each cell we can represent by creating a current dipole vector. Okay, and the ECG is the vector summation of all of these current dipole vectors as measured at the outside of the heart. Okay, so here's a diagram that effectively kind of shows this. If you were to isolate the action of the myocytes in various different regions of the heart, you would get a whole bunch of different shapes that look very similar to what we described earlier. But due to the relative density of myocytes in various regions of the heart and how long they're activated for and so on and so forth, when we vector sum all of these different waveforms, we eventually get the characteristic ECG waveform. Now here's an animation. I hope you'll be able to see it on the video. I'm not sure how PowerPoint will export this, but effectively what happens is as the heart is beating, as the big ventricles end up pumping, we get this really big spike of activity. We get a little bit of repolarization events here at the end of the heartbeat cycle, and so on and so forth. Okay, so again, it's kind of a distributed electrical action through the heart. They obviously don't all beat at the same time, otherwise the two stroke action won't really work as well as it should, and we get our classic ECG waveform. Now the ECG waveform has some very signature morphologies, as we call them, or shapes or parts of the ECG waveform, and they have names. Okay, so the P wave is this little bump over here. This is the wave that's created from atrial activation, so it's a little smaller than what happens next, which is what we call the QRS complex, and this is what occurs when the ventricle myocytes depolarize. So this is the big action, because again, the ventricular action is the big pump inside the heart. Okay. Now after that happens, we get the T wave, which is effectively what we measure when the ventricles repolarize themselves. Now here's just another diagram effectively trying to describe how the vector summation of the heart is happening. I'm not going to spend too much time on this, but if you like, it's a useful diagram to kind of study and think through, and it might help reinforce the vector summation concept that we're talking about here. So what's interesting about this is the electrical activity of the heart is measured on the outside of the body. We place electrodes on the outside of the body, and we're trying to do vector summation. Now, obviously, how we do vector summation will depend on where our points of references are, right? If we put two electrodes at certain points on the chest, or then we move them to different points on the chest, we're going to be summing the vectors differently, okay? And what this means is that ECG will depend on electrode placement. Okay. Again, it's a vector summation. What we are doing is we're effectively trying to build the projection of vectors between two different spots on the body. Okay. Now, a couple notes. The potential will generally increase with increasing separation between the electrodes. The further apart they are, the further the vectors have to travel, admittedly, but the resulting waveforms will be more different when you measure the potential between them. And the potential increases if the average distance to the heart also increases. Okay, so what do we do? Well, we need some sort of consistent placement methodology in order for us to get consistent results. Okay, now before we do that, we need to get a little bit of terminology through here because a lot of electrical engineers kind of use electrodes, leads, and probes as kind of analogous, but in ECG speak, there's a difference. Okay, so in ECG speak, an electrode is a single element. So in this diagram here, A and B are electrodes. Okay, now a lead is a pair of electrodes measuring the potential between them. Okay, so a pair of electrodes comprise a single lead. Okay, now in this case we're measuring the voltage, for example, between points A and B. We're going to call this a scalar lead. Okay. Now, clinically, when we get an ECG, and you go to the hospital, you get an ECG, they typically will measure what we call a 12-lead ECG. Okay, so what we mean by 12-lead ECG is we put 6 electrodes on the chest in very specific regions, and then we have 4 limb electrodes: one right arm, right leg, left leg. Okay. Now they don't have to be on the wrist. It could be oftentimes in the kind of the upper chest near the shoulders, or on the abdomen or something for the right and left legs. But this is the general diagram here. Okay. Now it's a 12-lead ECG. We have 6 chest electrodes and 4 limb electrodes. If you do some math here, 6 plus 4, that's 10. That does not equal 12. Okay. So what's going on here? Okay, so it's slightly more complicated than it seems at first glance, but once you understand it, it's fairly straightforward. Okay, so what we have are several different lead types. So again, only 10 electrodes, but 12 leads. Okay, now 3 of our leads are what we call bipolar leads. Okay, so lead 1, for example, is the measurement between the right arm and the left arm. Lead 2 is the measurement between the right arm and the left leg. Lead 3 is the measurement between the left leg and the left arm. We call this a bipolar lead because it is measuring the difference between 2 specific spots. Okay. Now, we also have what we call augmented limb leads, which is effectively measuring the voltage on, for example, the left arm with respect to a summed voltage of the 3 limb leads, if you will, and that's basically summed with specific angles to represent some internal node, if you will. Okay, and we call these unipolar leads. And then we also have our chest leads. These are our 6 chest leads. They're placed in very specific regions. We call it V1, V2, V3, V4, 5, and 6. They're placed at very specific regions around the surface of the chest here. And so we have 3 limb leads, 3 augmented limb leads, and 6 chest leads. And so that does sum up to 12. So this is a classic example of what would be measured through the 12-lead ECG. And you'll notice here that the morphologies of these waveforms, they look different, right? Lead 2 kind of looks fairly like this classic ECG waveform we've been talking about. V5 kind of looks pretty classic like that as well, maybe V6 as well. But some of these other leads look a little different. Okay. Now the reason for this is because the way that we measure ECG is effectively taking a cross section or a projection of the vectors between different spots on the body. And when a clinician, a cardiologist, is looking at this, they are looking at various cross sections of the electrical activity of the heart, and so they will give you different information about different pieces of the heart, about the different valves and so on and so forth. So this 12-lead picture is a classic clinical picture, and it does give a lot of useful insight. Now, if we only gave you lead 2, for example, they may not be able to, a clinician may not have enough information to perform a deep diagnostic on what's going on in certain areas of the heart versus others. So that's why we have all these different leads. Okay, so now we understand a little bit better on how the heart works, both mechanically and electrically. How do we build a system to measure these electrical parameters? Okay, so it turns out if you go ahead and put electrodes on the body in various of these different lead configurations, what you'll find is that the QRS complex has an amplitude on the order of about 1 millivolt. Okay, the bandwidth of a signal is on the order of about 150 hertz. Some people will design a little higher, 250 hertz, something like this. Okay, but that's effectively in the right ballpark for ECG. And we'll also tend to find that we have a lot of 60 hertz noise. Okay. Now the amount of, and I guess this is not really noise, it's interference. Noise implies non-deterministic. 60 hertz is deterministic in theory. Usually it's treated as some form of noise, but it technically is actually interference. And depending on the placement of the body with respect to the AC mains, the type of instrumentation, is the instrumentation itself plugged into the wall? What's the coupling between the wall electronics or the wall power and the actual instrumentation electronics, etc. But it's not unheard of to get 60 hertz interference up to 10 hundreds of millivolts, even 10 volts is not completely crazy and unheard of. In fact, it's actually a very useful experiment. If you just go up to an oscilloscope and just touch one of the leads there, what you'll find is you actually will see a significant amount of 60 hertz on there if you don't do a specific job of filtering or actively grounding yourself. Okay, so given that we do potentially have a lot of 60 hertz interference, what kind of common mode rejection ratio do we need from our instrumentation amplifiers in order for them to work effectively? Okay, so let's just imagine for the purposes of calculation that we need a signal to noise ratio of greater than 40 dB after amplification. Okay, and let's say that we are given an ECG signal. VIN differential signal is 1 millivolt. That's our ECG signal. And VI in common mode is something like 1 volt. Okay, so let's say we have 1 volt of 60 hertz interference. We have a 1 millivolt ECG signal. So we can say is the SNR, or I guess technically the signal to interference ratio, we'll just call this SNR just to be a little loose about this, is minus 60 dB. Okay, so we need 40 dB. So SNR out is going to be VI differential times the differential gain divided by VI common mode times the common mode gain, which is effectively equal to the common mode rejection ratio times VID over VICM. Okay, so in dB, if we go to units of dB, we say that SNR out equals CMRR plus SNR in, and this has to be greater than 40 dB, which means that we need a common mode rejection ratio of greater than 100 dB. Okay, 100 dB is, this is a logarithmic number. It's a very large number. Okay, and so we have to be clever about the way we design our instrumentation amplifiers in order to reach that type of common mode rejection ratio. And we're going to talk about that later on in this course. Now, the other thing we have to think about is how are we physically interfacing to the body? Okay, so we want to put an electrode on the body. The body is, we can only, if it's non-invasive, we can only interface with the skin or the epidermis. And we want to put some sort of metal, some sort of electrode, some conductor onto the body. Now, because the epidermis is not a flat planar surface, it's smooth, it's curvilinear, it's can be rough. It's not a classic electrical connection of a type of surface. What we typically do is we will build an electrode out of some sort of metal, typically silver or silver chloride, something like this, and we'll connect to the epidermis or the skin via an electrolytic gel. Okay, and what this gel effectively does is it provides a conformal contact to the curved nature of the skin to provide a good low effective impedance. Okay, now this is in contrast to something what we call a dry electrode, which would be basically just the metal, take out the gel. It's going to have a much larger input impedance typically. Okay, now For very simple modeling, for projects and homeworks and so on and so forth, we'll probably get a little bit more complicated than this. But for very simple modeling, we can take this effective circuit model that's drawn here from the Webster textbook and replace it with the 100 kilo ohm resistor. We'll get a little bit more complicated later, but for now, good enough. Okay. Now, one thing that's really interesting is that the effective resistance of the electrode is dependent on a lot of things and therefore can vary significantly between neighboring electrodes. Okay. And this turns out to be really important because if we don't have perfect matching between neighboring electrodes, this will actually further influence what kind of amplifiers and instrumentation we're going to need to build. So let's take a look at a quick example here. Okay, so we want to measure the voltage between the right arm and the left arm, VA and VB, and our reference point is going to be the right leg. Okay, or sorry, the left leg. Now let's imagine that we have some model of the electrodes. We'll call that R1 and R2. Okay, and furthermore, we have some input impedance into our amplifier. Now let's imagine for the purposes of this example that this is a perfect amplifier. It has just the right amount of gain. Its common mode rejection ratio is infinity, which is greater than 100 dB. So our 60 hertz problem is not a problem, at least from the amplifier's perspective. But let's imagine that the impedances between the two electrodes are not perfectly matched. Okay, so what happens? So let's calculate Vin1. This is going to be equal to Rin divided by R1 plus Rin. Again, Rin is the input impedance of the amplifier times VA here. Okay, so we can do a little bit of algebra here. 1 over R1 plus R1 over Rin times VA, which is approximately equal to 1 minus R1 over Rin times VA. If Rin is much greater than R1, which is typically what we'll want to design our systems to be. Otherwise, we have a lot of attenuation before we even get to our amplifier. Okay, so we can then say as Vin1 minus Vin2 is equal to 1 minus R1 over Rin times VA minus 1 minus R2 over Rin times VB. Okay. All right, then if we can say if VA is equal to VID over 2 plus VCM plus some common mode interference, and similarly VB is equal to minus VID over 2 plus some common mode interference, what we can say here is that Vin1 minus Vin2 is equal to VID over 2 plus VCM times 1 minus R1 over Rin minus VID over 2 plus VCM times 1 minus R2 over Rin. Okay, so we can collect a few terms here. We can say the differential term is 1 minus R1 minus R2 over 2 Rin plus VCM times R2 minus R1 over Rin. Okay, now there's a really interesting point that happens here. So R1 minus R2, R1 and R2 are supposed to be matched, but even if they're not, this will be should be a small number. It's divided by a large number, so this is effectively 0. Okay, so in other words, what's happening here is that the input from the body to the input of the amplifier before amplification, we get a differential signal that is effectively the differential signal that we're looking for. Okay, now keep in mind, we've done Vn1 minus Vn2 here. This is the differential signal at the input to our amplifier. But despite it being the differential signal, we have a common mode component that's looking like a differential mode signal. Okay, so the amplifier has infinite common mode rejection ratio, but because we have electrode offset impedances or mismatched electrode impedances, we actually get a common mode signal appearing as a differential mode signal in front of our amplifier. So despite having infinite common mode rejection ratio in our ideal amplifier here, we still have common mode signal that's entering the circuit. Okay, so this is not good. All right, so let's go through our SNR calculation again. For 40 dB SNR, we say that VID over VCM times R2 minus R1 over Rn has to be larger than a factor of 100. That's 40 dB in voltage units. Okay, which means that Rn has to be larger than 100 VCM over VID times R2 minus R1. Okay, so let's just go through the example that we discussed earlier. For VCM equals 1 volt, VID is 1 millivolt, so we have 60 hertz common mode interference at 1 volt. Our ECG signals at 1 millivolt. Let's say R1 is 100 kiloohms and R2 is 110 kiloohms. So not a huge difference between R1 and R2. What this means is that Rn will have to be larger than 1 gigaohm. Okay, so this turns out to be non-trivial to get an input impedance to our instrumentation amplifier of larger than a gigaohm. Okay, and so that's one of the challenges we're going to have to face when we are designing our instrumentation amplifiers. Okay, now it turns out that there's other solutions other than just making a huge input impedance circuit. We're going to talk about that in the next lectures on active grounding of the body through a driven right leg circuit. Okay, but for now, I think this nicely motivates the need for, despite having what appears to be modest specifications, it turns out that instrumentation amplifiers, despite having low bandwidth, are quite tricky to design, particularly if you want low noise and low power, and you want this to operate reliably in the presence of lots of interferers.